Right then, let's talk about one of science's most iconic charts, the periodic table. You've seen it on classroom walls, right? But the story behind it is this incredible quest for order in a seemingly chaotic universe.
And you really can't overstate its importance. Just listen to Nobel laureate Glenn T. Seaborg. He called it arguably the most important concept in chemistry. Why? Because it proves that the elements, the very building blocks of everything, aren't just a random jumble. There's a pattern, a family resemblance.
That really sums it up, doesn't it? But it does beg the question, how on earth did we get from this total mess of elements to this? Well, this elegant and beautifully organized map of matter? That's the journey we're going on today.
So, our story kicks off with what you could call the elemental conundrum, a real puzzle for 19th century scientists.
Okay, so picture it. The 1860s. By 1865, chemists had managed to identify 63 unique elements. Now, that was more than double what they knew at the start of the century. Things were getting a bit out of hand, and there was this desperate need for a system, some way to make sense of it all.
And to be fair, people were trying. Some really brilliant minds were starting to see patterns. You had Johann Dobereiner back in 1829 noticing these little groups of three, his triads. Then came others like Deschamps-Courtois and Jean Newlands. They were all getting warm, circling a fundamental truth. But no one had quite cracked the code.
Let's look at Dobereiner's law of triads. He spotted that for some groups of three, like lithium, sodium, and potassium, the middle element had an atomic weight that was pretty much the perfect average of the other two. I mean, that's a fascinating clue. But the problem was, it only worked for a handful of elements.
And then there was John Newlands. Now he arranged the elements by their atomic weight and noticed that their properties seemed to repeat every eighth element. He compared it to the octaves in music. A brilliant idea, really. But it all sort of fell apart after calcium. So the search for that one universal system had to go on.
Now, all these early attempts were absolutely crucial stepping stones. But then comes the hero of our story, a Russian chemist named Dmitry Mendeleev. And he took this whole quest for order to a completely revolutionary new level.
So in 1869, Mendeleev publishes what he calls the periodic law. His fundamental idea was this: the properties of the elements repeat periodically if you arrange them by their atomic weights. He lined them all up by increasing weight, but, and this is key, he also made sure to put elements with similar properties into the same vertical columns. But here is the stroke of absolute genius. Mendeleev wasn't bothered by things that were missing. If his pattern said there should be an element in a certain spot, but none was known, he just left a gap. He had the sheer audacity to predict not just the existence, but the properties of elements that no one had even discovered yet.
And would you believe it? Here is the ultimate proof. He predicted an element he called Eka aluminum. He described its atomic weight, its density, even the chemical formula of its oxide. Years later, an element called gallium was discovered, and its properties were an almost perfect match. I mean, look at that. Astonishingly accurate. That one success made him and his table world famous.
So, Mendeleev's table was a massive triumph, no question. But there was still a piece of the puzzle missing. The big question remained, why did it work? What was the underlying reason for this beautiful, repeating pattern? That was still a complete mystery. The final piece of the puzzle arrived in 1913, thanks to an English physicist, a chap named Henry Moseley. He was working with X-rays, and he discovered that the true organizing principle wasn't atomic weight after all. It was something deeper, more fundamental, the atomic number, which, as we now know, is the number of protons in an atom's nucleus. And this was the fundamental shift that changed everything. See, Mendeleev organized by weight, which worked most of the time. But there were a few odd spots where it didn't quite fit. Moseley's discovery of the atomic number provided the true order, and it resolved every single one of those little exceptions. It just tidied up everything perfectly. And this led directly to the modern periodic law, which is the foundation of the table we all use today. It states, the physical and chemical properties of the elements are periodic functions of their atomic numbers. Simple, elegant, and most importantly, correct.
Okay, so we've got our perfectly ordered table. Brilliant. But why does this matter so much? What can we actually do with it? Well, this is where the table goes from being just a chart to an incredibly powerful tool.
You see, the table's structure isn't just a catalog, it's predictive. Just by knowing an element's address on the table, its position, we can make very good guesses about how it's going to behave. These predictable patterns are what we call periodic trends.
Let's take atomic radius, for example, basically the size of an atom. As you move from left to right across a row, the atoms actually get smaller. That's because the nucleus gets more positive, pulling the electrons in tighter. But as you go down a column, the atoms get bigger because they're adding whole new layers or shells of electrons.
Or, what about electronegativity? That's just a fancy word for how badly an atom wants to grab electrons from another atom. This power increases as you go across the table to the right, but it decreases as you go down. Understanding a simple trend like this tells the chemist a massive amount about how an element is likely to react. It's why we can design new medicines and engineer incredible new materials.
So there you have it, from a chaotic jumble of just 63 elements to a beautifully ordered map of all 118 known to us today. The periodic table really is a monument to our human quest for understanding. But, as we continue to create new, even heavier elements in labs, it makes you wonder, what other secrets are still hidden, waiting to be discovered within this fundamental map of our universe?